Okay, good. So let me continue where we stopped last day. Okay. So basically, what we ended the lecture the last day is something that is called the window problem. Okay. And this is an intrinsic limitation of every simulation that you want to do. So basically, you have an infrared cutoff. This is the volume of your lattice. Okay, how big is the simulation in Fermi? Okay, this thing has to be much larger, for sure, than the cutoff, the lattice spacing. This is clear, but this much larger means 5 or 10. So this is easy, the number of points. The problem is that for the determination of alpha s, okay, you need to put in between the scales that you want to explore. Okay, so this is 1 over mu, okay, and has to be in between. Okay, and this limits the range of scales over which you can do physics. This is true for alpha s or for the determination of the proton mass for anything. Okay, the delicate point about alpha s, or in fact whenever you are using perturbation theory, is that you need to vary this scale, okay, in such a way that g of mu varies enough. Okay, so as we said, g of mu is not really a running coupling, it's a slowly walking coupling because it goes only logarithmically with the scale mu. Okay, and these two much larger are very hard. Okay, so two much larger than is very difficult to resolve. Okay, on a single simulation. So we did some example, okay, where the physicist, in order to really reach the electroweak scale and be able to do a continuum limit, would need lattices of tens of thousands of points in each direction. The cost of this is very high. And if not, you have to make compromises. Okay. So in the exercises that I think that they are online now, there is one example. Is imaginary futuristic computation where some physicists have managed to do simulations in lattices 400 cubed times 800, so this is very, very large. Lattice spacings of 0.01 Fermi because they have solved topology freezing and they have dealt with autocorrelations, maybe thanks to the future algorithms that we have been seeing today by Jacob and by Tesh. Okay, but despite of that, you would see that this simulation is not quite enough to get a good precision in alpha. Okay. And this is the purpose of the exercise. It's a relatively simple one, and I invite you to try to do it this evening and ask me any questions. Okay. So, although we have said that this is a problem especially to determine the coupling, okay, and alpha s, it is not the only place where it appears. Basically, it is whenever you need to match with perturbation theory. And we can do many hadronic physics without worrying with perturbation theory. As I said, you can compute the hadron spectrum, you can do all these things, but there are many other interesting things in flavor physics, for example, that require to deal with renormalization. Okay, so let me put a list. Okay, so one of them is quark masses. If you look at FLAC, okay, you will see that people prefer to quote the quark masses in the MS bar scheme at 2 GeV. So the fact that here is written MS bar, that is what is interesting for phenomenology, automatically implies that you need to match with perturbation theory. And although you don't do it at 2 GeV, you do it at 3 or maybe at 2.5, because this is where you can take a continuum limit with current lattices, still these scales are quite low. Okay. In any case, perturbation theory for the case of quark masses seems to be much better behaved than for the case of the coupling. Okay, and I would say that here this is not a major problem. Okay, but if you look at FLAC, there are other places. Okay, so another one is the meson oscillation parameters, meson mixing. Okay, so these are the BK or the BS parameters. They are typically also quoted at 2 GeV in the MS-bar scheme. Okay, and this means that if you want to analyze this, you need to match with perturbation theory. Okay, in this case, the relationship with MS-bar is not known with very high loops, like in the case of the quark masses. Here we have these RI-MOM schemes where things are known up to 4 loops. Here we have really 1 loop only. Okay, and there are some discrepancies in the 4 fermion operators, the ones that are relevant for BSM physics. Okay, and I would bet that that part of the guilty of these discrepancies has a bit to do with the fact that you are using perturbation theory, 1 loop perturbation theory at 2 GeV. Okay, and this is dangerous. So I think that there is things to be thought and done here, and all these things can be thought in the same way that we said that the proper way to understand the extraction of the coupling is to think about the RGI invariant, that means the lambda parameter, and that it can be defined non-perturbatively. All these quantities also have RGI invariants. Okay, in the case of the quark masses, we always tell them with a capital M. Okay, in fact, in the case of the quark masses or of BK, they are on top of having a universal relation. They are also scheme independent. Okay, and also I think that there is a B hat here for this for the RGI invariants. But in any case, there are RGI invariance versions of this. And this can be defined non-perturbatively in the same sense as lambda. Okay, you will have an expression that has an explicit integral, and when you use perturbation theory, there are corrections to this expression that are order g to some power. Exactly the same happens here. And taking the limit g to 0, I think that in fact for the general lattice community, when the precision increases as we are doing, has to be taken seriously. So really, in the same sense that it is not good enough today to do a simulation with a single lattice spacing and then trying to argue that cutoff effects are at most 2%, okay? I think that it's not good enough to do simulations and match with perturbation theory only at 2.5 GeV and argue that perturbative corrections are smaller than that. One should really take this more seriously, and I think that there are papers to be written about this in the future, okay? So there is room for doing stuff there if you take the same point of view, okay? Very good. So now what this lecture is going to be about, okay, this is a small recapitulation, is about a solution for this, okay? This is will be explained in the context of alpha S, but similar techniques have been applied to these other problems, so you can check, okay? So basically, the problem of the window problem is that you have these two inequalities here. And having one of them is okay, but having two of them is just too hard, okay? It's very difficult to keep the volume very far apart from the renormalization scales and very far apart from the lattice spacing. And then you are forced to do compromises. Either you take a not so good continuum limit and then 1/μ approaches A, or either you explore things that are close to the volume and then you argue that the volume is not that important and that perturbative corrections at these low scales are not that important, okay? But the solution, in fact, to this, explained like this now, is quite obvious. It's also quite long. Is instead of doing this, what we are going to do is to remove one of the inequalities. So we are putting here a factor. This is for convenience. It's a number order 1, let's say 1/2 or something like this, C times L. And we are going to identify this with the renormalization scale. And of course, we always want to take the continuum limit, okay? So it is still true that this has to be much larger than the lattice spacing. So now, by magic, you don't have two much larger than, you have only one, okay? And this is doable. The only thing that I need is that L over A is 20 or something like this, and the renormalization scale is given by the volume, okay? So of course, this is blah, 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 okay? Unless I tell you that this is really a working solution and that it can be useful to determine lambda, okay? So I claim that this is the solution, okay? And it's in fact an old idea. It has almost 30 years old, okay? It comes back to a paper of Uli Wolf and Martin Luscher, Peter Weiss, okay? of using these finite volume renormalization schemes. So basically, what is behind this idea is that there is a lot of freedom to define the coupling. We said that you could use the quark-antiquark potential or the gradient flow. The coupling is not a physical object. It's something that you use to renormalize the theory. You write your expressions, your quantities, in terms of this renormalized coupling. And if you choose one or the other, it doesn't matter, okay? All the results will be the same. So how would you implement this scheme? So this scheme, in principle, can be done with any of the couplings, in principle, that we said yesterday. So for example, what you do for the QQ-bar coupling is that you put your quark and an antiquark in a box, okay, that has a finite extent, L, okay? And now, your QQ-bar coupling, exactly the same as the other day, at the scale mu, you say that this is equal to the same, is r squared times the force between the quark and the antiquark. There is a number here. Before it was this 4/3, okay? Now, since you are in a finite volume, to compute this number actually requires a computation in finite volume. I'm not going to worry about this, but it's no longer 4/3. It's another number that will depend on this c that you choose here. And then, for example, I will declare that I will put the quark and the antiquark a distance, okay, that is equal to L/2, okay? And this is my renormalization scale. So, the idea here is somehow very simple. If I want to explore how much is the force between a quark and an antiquark at a tiny distance, okay, let's say at the electroweak scale, to probe that it is really weakly coupled, it's very difficult to simulate a whole 6 Fermi lattice, okay, to do this. So what I do is I put this QCD in a tiny box, okay? And if I want to explore a longer distance, I make the box a bit larger. If I want to explore a longer distance, I make the box a little bit larger, okay? The universality of QCD guarantees that this is a good definition. In other words, if you come back to what we said the first day, there were 3 conditions to define a coupling. It has to be dimensionless, it has to depend on a scale, and it must have a continuum limit. All these things is true if you analyze the force between a quark and an antiquark in a finite volume. You don't need it to be in an infinite volume, okay? So this is the idea behind. This is a coupling as good or as bad as any other, okay? And in principle, it can be used. You can compute it, okay? And the good thing is that you can compute it for R very, very small. You can compute it at 1000 GeV, it doesn't matter, okay? Very good. And you can compute it at 1000 GeV, I mean, with a reasonable number of points, with lattices of 10, 30 points, okay? Not with 1 million points, okay? Very good. So, how you can do the same for the other couplings, huh? For example, the GF coupling, we said that we were smearing our fields for a distance that was given by the flow time, and this was used to define a gradient flow coupling, okay? It was t squared E of t. This is always the same because this is the combination that is dimensionless. Now the number that is here is going to change. Before it was, I don't remember, 4 pi over 3 or something like this. Now this number will change. And the only thing that you do, again, is to relate the renormalization scale with the length. So square root of 8t, that is equal to 1 over the volume. You say that this is equal to CL, okay? And this C, typically in practice, we use values like 0.3 or 0.4 or 0.2, so this thing, okay? So this is telling you that this radius of smearing is smaller than half of the lattice. It's 1/3 of the lattice or something like this. These are the typical cases that we use, okay?
So the number changes because you're not in a big volume.
Exactly. So this number here, how is this number determined? This number was determined with the condition, I mean, this is a constant. So in principle, it is not needed, but in order to have these universal coefficients of the beta function and all these things well behave, we want that this, when it goes in perturbation theory, okay, is equal to alpha ms bar of mu, okay, plus corrections. So we want a 1 here, okay. So the trick to compute these numbers is very easy. You compute this in a finite volume. So instead of having integrals over the momenta, now you have sum over the momenta. And when you compute this on a final volume, you adjust the coefficient in front such that the perturbative series of this object starts at alpha. not at 2 alpha or at alpha over 3 or at any other number. Okay? Here the same. You do a perturbative computation of this, and you compute this constant in order that you guarantee, okay, that the perturbative series, okay, starts in alpha and not in 7 pi alpha. Okay? So this is how you compute these numbers. Okay? So once you have that, you have proper couplings, okay, and they are as good or as bad as any other. Okay? So this sounds very easy, but I have to deal with a couple of things. Okay? So, okay, let me write this thing here, and I can keep it for a bit of a longer time. So, first of all, the only thing that I have claimed is that these are valid coupling definitions. I examine QCD on a finite volume. Okay? Now, when you do the finite volume thing, okay, you are not doing large volume, the choice of boundary conditions is relevant. Okay? So, in infinite volume, it doesn't matter if you use open, if you use periodic, you can put twisted boundary conditions for the quartz. All these are finite volume effects that can be interesting, but they are not really relevant in the infinite volume limit, okay? And we try to work always in very large volumes. So here, when you do QCD on a finite volumes, the boundary conditions are very relevant, okay? And this is a technical question, okay? But more important than anything, okay, is that I have still to show you, to tell you, a working technique in which this kind of couplings solves the window problem. Can I compute lambda using these definitions of the coupling? Okay? So in other words, does this really the window problem? Okay? My claim is that yes, okay. I will try to explain this, okay. So, there are two components of this, okay. If you remember the formula for our lambda, we said that lambda in a scale mu 0, okay, this is true in any scheme, is an exact relation, is 2b0 g squared of mu 0 times 2 minus b1 divided by 2b0. Okay, let me check this because I will not write it correctly for sure. Then you have here an e to the minus 1 divided by 2b0 squared g squared of mu 0. And then you have the exponential of minus the integral between 0 and g of mu 0 dx. And here I have 1 over beta of x plus 1 over b0 x cubed minus b1 divided by b0 squared x. Okay? So this formula is exact. Okay? So now the coupling will be one of these finite volume couplings. Okay? And in order to compute lambda, there are two things that you need. Okay? Let me write them in a different color. Mu 0, so you compute lambda in units of some scale, that is where your coupling is known, okay? So I need a way to compute this. I need to relate this scale mu 0 with the proton mass or with a physical input, okay? Okay, very good. And there is another thing that is needed, that is this beta function. Of course, this I don't want to put perturbation theory there, I want to compute this non-perturbatively. So I should find a way to compute this part of the integral at least, okay, using perturbation theory. And this is what the finite volume schemes can do. Okay? So what we are going to go first is trying to explain how these finite volume couplings allow you to do these two things. Compute integrals of the beta function and relate it with a physical quantity. Okay? And then later, I will go into the details of the boundary conditions and how these couplings are precisely defined. Okay? This is more technical, And it's important, okay, because if not, when you see papers and people talking about this, they do crazy things. There are reasons for these crazy things, okay, although they are no longer explained in the papers. Okay? They were in the old papers, okay? Very good. So, the key ingredient to do the first part, let's start here, okay? Okay, is a character that is called the step scaling function. Okay? So the step scaling function is like a discrete version of the beta function. Okay? Okay, very good. So, what is the definition of the step scaling function? The usual name for the step scaling function is sigma. Okay, it is a function that has one argument, u. Okay, and when you compute it, it gives you the coupling at a scale mu over 2. Okay, under the condition that u is equal to the coupling at a scale mu. Okay. So, what is this coupling doing? This coupling is taking the value of a coupling at one scale, okay, and then it spits out the value of the coupling at a scale that is a factor 2 smaller. Okay. So, in the context of these finite volume schemes, what I would do is I compute with my GF, okay, the coupling at some volume L, okay. This thing gives me u. That is the value of the coupling measured at this scale. For finite volume couplings, we usually do an abuse of notation. Since the coupling, okay, the scale, is proportional to L, okay, we many times call this G squared of L. It doesn't matter, because there is a one-to-one relationship between L and U. But it is not the same function, as you know very well, but this is an abuse of notation that you will find almost everywhere, okay? So you claim that this is a coupling defined at this scale, and you can give the scale in terms of mu or in terms of L, okay? And depending on the context, I hope that is clear. If not, you ask me. So you measure the coupling at this value of the volume, okay? And this gives you a value of u. Now, if you apply the function sigma, what it does is giving you the value of the coupling in a volume that is 2 times larger than the original one here, okay? And this will be sigma of u to L or mu over 2, doesn't matter, okay? So I will finish my coffee and I will give you 20 seconds so that this sinks in, okay? So you get an idea of what this function is doing. Okay, very good. So what does it do? It takes the coupling at one scale and it gives you the coupling at half the renormalization scale or twice the volume. Okay, so my claim is that if you know this function, if someone comes to you and tells you the function in NF equals 3 QCD is u plus u squared plus blah blah and gives you a complicated functional form, then there is no problem in computing this thing here, okay? So you can compute this integral. Let me show you how this is done. It is done because this step scaling function is changing the renormalization scale by a factor of 2. That means that this relation is exact. So let me write what are the arguments here. Sorry, G. Okay. Why is this? It's because the original renormalization group equation that we started with, okay, was claiming that the beta function has this equation. Therefore, you remember back in the past, if I write the d mu here, this is equivalent to d mu divided by mu is equal to dg divided by beta of g. And the integral version of this is telling you that the integral between g mu1 and g mu2 of the beta function is equal to the logarithm of the ratio of scales. Okay? So basically, if I know that the ratio between two scales is 2, then the integral of the beta function between the value of the couplings at these scales has to be log of 2. Very good. So
you could have taken 3 as well.
You can take 3, and you can take 1/2. Okay, you can take any number that you want. Okay, yeah. So the 2 is customary. People have used other values. You cannot use pi. Okay, and this is related with what we will go to do after. Okay. But yes, in principle, this is arbitrary. It's a discrete version of the beta function. We can put a number arbitrary there, s. Okay, and then this is still true. Okay, very good. But yeah, you're right. Very good. So, what does this mean? This means that now the difficult part here, because this part of the integral is easy to do analytically, there is no problem. Okay? So the difficult part, that are pieces of the integral of the beta function, I can compute them in this way. Okay? In other words, I want to start here from a scale mu0. Okay? So the difficult part is to compute this thing that is the integral between 0 and g of mu0 dx beta x. Okay? But I know that this integral, I can write it as the integral between 0 and g of mu0, okay? Of course, this is true for any integral, okay? I split the integral between 0 and g of mu0 in an integral between 0 and g of mu1, okay? And the integral between g1 and mu0. And now if I choose this mu0 and mu1 exactly by a factor 2, I know that this thing here will be log of 2. Okay? So, what I am doing with this, okay, is pushing mu1, okay, now, okay, maybe. So now mu1, okay, is equal to 2 mu0. I have pushed the integral that still I don't know how to compute to higher energies, a factor 2 higher. Okay? And I can repeat this thing here. I will define a mu2 that is equal to 2 mu1 is 2 squared mu0, okay? And I get another log of 2 here. Okay? And I can do this 20 times, and I will get a 2 to the 20 factor in a scale. Okay? And then the last mu20 will be a very, very perturbative number. Okay? In fact, with 10 steps, 2 to the 10 is 1000. So you go from 200 MeV to the electroweak scale. Okay? So this is an exponentially efficient solution to solve the fact that the perturbative uncertainties only decrease logarithmically. Okay? So all in all, this original formula of lambda over mu0 is just 2 to k. K is the number of steps that you do of the step scaling function. Okay? And now here, instead of putting g of mu 0, I have to put g of mu k, that is 2 to the k mu 0. And here the integral that remains is only up to 2 to the k mu 0. Okay? Sorry. Okay, exponential minus. Okay. So, okay, some of you are worried that I have been cheating you because there I have only said how to do the integral of this piece. Okay, you still have to do the integral between mu 1 and mu 0 of this other piece here. Okay, but this is very easy to convince yourself that the only thing that does that is in these two pieces substituting g of mu 0 by g of mu 1, okay, and g of mu 2, g of mu 3. Okay. And now you get an explicit factor 2 to the k that comes from the accumulation of the logarithms of 2 here, log of 2 plus log of 2 plus log of 2, every time that you apply one of these steps. This with the exponential gives you 2 to the k. Okay. So now what is the good thing about this expression? Why this solves the window problem? Because now this piece here that still remains and I need to compute is an integral between 0 and g to 2 to the k mu 0. And here it will be a very good approximation to use the beta function in perturbation theory, okay? Because this is really 100 GeV. And if 100 GeV is not enough, I go to 200, and if it is not enough, I go to 1000, okay? It doesn't matter, because here you don't need to cover all this range of scales with a single simulation, okay? Each determination of the step scaling function allows you to jump a factor 2 in scales, okay? Yes?
I think I got a little lost. So we are doing like a matryoshka of simulations, and
Yes.
each mu, it's like the mu belonging to each simulation.
Yes, it's the volume. When you think mu in these schemes, you have to think about the volume. So you do simulations with a volume, you start from a large volume, okay? Then you go a factor 2 smaller, then a factor 2 smaller, a factor 2 smaller, okay? In each of these cases, okay, your coupling gets reduced, okay? Because you are measuring a shorter and shorter distance, okay? And each of these jumps from one simulation to a factor 2 smaller gives you one factor 2 here, okay? Simply because mu 0 you are multiplying it by 2, okay? And now in the end you end up with a tiny box, a femto universe, super, super small, and their perturbation theory is very good. This is a universe where QCD is basically free quarks interacting through gluons, okay? And then you apply perturbation theory there, okay?
And we arrive to this perturbation theory because it's more easy to work.
What is more easy is to compute this integral when this scale is very high. If you start in your large volume, perturbation theory is useless there. This is a box with not with quarks, but with protons and pions, okay? So you need to go to very small box where there are no protons, there are nothing, there are only quarks and gluons. So this is physically what is happening. Okay? Yeah?
Why a factor of 2?
We will go to this, but yeah, it's a very good question. Yeah. Okay? Okay, so what we have been doing until now, it's only telling you that if God comes here to Earth and give us the step scaling function, then I know how to compute this. Of course, I still haven't told you how you compute this, okay? So, yeah, of course, there are many things that if someone tells us, we know how to solve things. In particular, I could have said that if you give me the beta function, I compute this. Yes, sure, okay? But the difference here, and the reason for this factor of 2, is that there is a way to compute this thing on the lattice that does not require huge lattices. And this is the key thing here. So once, okay, again, we'll drink some water. I leave you 30 seconds to sink in. If you have the step scaling function, you solve the problem. Now we have to do something else. It's finding a way to compute this step scaling function on the lattice. Okay? Yeah?
I mean, if you said you do different simulations with different box sizes, but they have to be at the same lattice spacing, right?
Yes.
This is a limit to how close. I mean, at some point you would in the limit L goes to 0, you will end up in a box which is one lattice size. You just want it-
No, 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 you don't do this. You are doing continuum physics all the time. So remember that we solved the window problem by making CL equal to 1 over mu, but this is always much larger than A. So we always use 20 points or 30 points. We want to do continuum QCD. Okay? I will show you how. Okay, so if this thing has sink in, now let me change. Now, the only thing that is left is giving you a way to compute the step scaling function. Okay? So, we do our simulations, okay, on the lattice, and for the moment, let me just assume that we are doing jump mills, okay? I mean, let me forget about quark masses for the moment. So in your simulation, there is only a single parameter that you input, that is beta, okay? So this beta, via renormalization, this is the Baire coupling, is related with the lattice spacing, okay? In other words, they are in 1/1 correspondence. I know that if I simulate the same beta, I am simulating the same value of the lattice spacing, okay? This is also true in QCD when you set up something that is called a massless renormalization scheme. But okay, so this thing is also true in QCD, but in jump mills it's much more clear. Okay. So now, what is the way to compute the step scaling function? So very good. I do my simulations. Okay. I have to choose my beta and my L over A. That is the number of points. This is the only freedom that I have in jump mills when I set up a simulation. I cannot do anything else. Okay, boundary conditions and all this, but this will go later. Okay. So now, I claim that by doing many simulations, I know that these simulations with these particular values of beta, okay, and these particular sizes, when I measure, I do the simulation and I measure the value of the coupling. So I measure, for example, the gradient flow t squared E of t, and I measure this as at a t that is exactly equal to 0.3 times L, okay? So that means if t square root of 8t is equal to c times L, when you do your simulation of the lattice, you don't get L and you don't get T. You get this in lattice units. But this thing is equivalent as saying, okay, that 8t squared over A squared is equal to C L over A squared. There is a square also here. Okay? So in other words, the thing that I get on the lattice, that is t over A squared, has to be equal to C squared divided by A L over A times square. So I know the value of the flow time because I know L over A. It's here in my table. Okay? So I read the value of t squared E of t at this value of t in lattice units. That is what I get in my simulation. I'm going to throw this. Okay? So when I do this, okay, I obtain the following magic numbers. So I obtain always the same number. Okay? Why is this? It's because the coupling depends on a single scale, L. Okay? So the fact that all these numbers are the same is telling me that I am making the number of points larger, okay, but the lattice spacing finer, in such a way that they compensate so that the volume is the same. Okay? So all this combination of parameters are some values of the lattice spacing that is implicitly given by A, okay, and a number of points in such a way that when I multiply them, the volume is constant. I don't know what the value is, but I know that it's constant. How? Because the coupling doesn't change, and the coupling only depends on L, up to cutoff effects. Okay, they are small. Is this clear? So basically, these are different boxes of the same size, okay, exactly the same size, with different number of lattice space, with different values for the lattice spacing. Okay, different resolutions, but the volume is the same because the coupling depends only on the volume. Okay. Now, what do I do to compute the step scaling function? Remember the definition. I compute the step scaling function by saying that I have to compute this in a volume 2 times larger. But now with this table, it is super easy to do this. The only thing that I have to do is keep beta the same, that means the same lattice spacing, and multiplying the number of points by a factor 2. So I take this value of beta, but instead of doing an 8 lattice, I do a 16 lattice. And I compute the value of the coupling at this volume that is 2 times larger. Okay? So very good. So I continue doing this. I continue doing this. Now I do my simulations on a 16 lattice. Okay? Let me write. So at this value of beta, I do now a 16, here I do a 20, here I do a 12, here I do a 32, here I do a 48. Hey?
16, 20, 24, not 20.
Oh, yeah, sorry. Yeah, sorry. Thank you. Okay? Sure. And if I do this, I obtain values, okay, that are 1.16469, 1.165, okay, 40. There are some errors here, okay. 1.16851, 1.17030, and 1.17157, okay. So you would say, okay, but if the coupling only depends on the volume, and here the volume is 2 times larger, why these numbers are not constant? They are not constant because it's true that this is true only up to cutoff effects. So we still have this thing here. Okay? But the way to remove this is just to take the continuum limit of these values. Okay? I do my usual A square, or model average, whatever you prefer to do. Okay? And then I can quote a value here that is 1.17325. With an error of 91. So what this procedure has done, okay, these few simulations, is allowing me to write that sigma of 1.4784 is equal to 1.17325. Okay. So I have given you a procedure of how to compute the step scaling function. Now I hope that the factor 2 is clear. Okay. Of course, there are other possibilities. I could use 3, but then these simulations become very expensive. I can use 3 halves, then okay, prime numbers are not good for lattice sites. Okay, well, okay. But there are other options for sure. For sure, you cannot use a irrational number. Okay. Very good. So all these simulations give me 1 point of the step scaling function. I need 10, okay, in order to cover 2 to the 10 range in scales. Okay. So is this really cheaper? Yes, it is way cheaper. Okay. So if you compare this value of the coupling, okay, is basically below the electroweak scale. This is 200 GeV. If you want to fit this in a single lattice simulation, you need 4 times 10 to the 4 lattice in each direction. So 4 times 10 to the 4 to the power of 6, and this I'm being very good with how we do the algorithms. Okay, this is much, much larger than 10 times this number of simulations. Okay.
This is the power of 6, right?
So a power of 2 or 4 is the volume. It's clear. Okay. Power of 2 extra is because of the correlations, okay? And then you need to do the integrator a bit finer, so probably there is a factor, another power more if you use fourth order integrators at least, and this is assuming that you have solved topology freezing and all these things. I mean, this is impossible basically, okay?
And this is how it scales with the volume.
This is if you want to do a single lattice simulation that reaches 200 GeV, you will need this number of points in each direction, okay? And this is how the computational cost scales with the volume being optimistic. Okay? Yes?
How come when we double the volume, G squared has the finite size effects, but originally we didn't have it?
It's not that we didn't, it's that I cooked up these numbers so that the value of the coupling is constant. Okay? So these numbers, you have to cook them. You have to do several simulations with 8 in order to tune, okay? So this is how it works. Cutoff effects is not that they are not here and are here, it's that in the way that you compute the step scaling function, I have decided it to be this way. I could also tune the values here to a constant number and then reduce the number of points by 2. Okay, there is no problem with that. Then these numbers will be constants and these will have the cutoff effects that I will need to extrapolate. This is not done in practice because it is more easy to tune to a value of the coupling on an 8 lattice than to tune on a 48 or a 32 lattice. Okay, so these are the cheap simulations, these are the expensive ones, so it's better to do the tuning here. But there is nothing fundamental in that. Yeah?
But I mean, if we have to do this 10 times, we would get something in the largest 2, where L is 24 times 2 to the 10.
Yeah, so you have to do this, let's say 10 times, okay, times 48 to the 6, so you compare these two numbers.
Yeah, but I mean, that's still a very large lattice, so it's still not.
Yeah, it's not easy. So there are several reasons why, first of all, these simulations, okay, we will go to this later, are much cheaper than the usual large volume simulations. The reason is that in a small volume, the Dirac operator has an infrared cutoff that is given by 1 over L. So this is like if you were simulating super heavy quarks, okay? So these are basically pure gauge simulations. Second reason why this is cheaper is that in fact you can do the simulations at m equals 0, at 0 mass quarks. And the reason is because the gap in the Dirac operator is not given by the mass of the quarks, it's given by the boundary conditions. So you are really doing a massless renormalization scheme. But this is doable, it has been done, I mean, 10 years ago, okay? So it's not something new, okay? Whereas this other thing, it will not be done in 10 years. So, I mean, this really is doable. I mean, if you multiply these numbers, the factor difference is huge. All these simulations is cheaper than, for example, generating a set of large volume ensembles like CLS.
Okay.
So this is much cheaper.
Sorry, just for completeness, if we set the scale with lattice spacing, that would be worse, I guess, right?
What?
If we set the scale with lattice spacing instead of the volume,
Yes.
that would be,
So you mean putting the equal here?
yeah, I mean, that could be
Then there is one part of this game, okay, that this recursion. I mean, there is people that have tried to do this in large volume in order to access large energy scales, but there is no such type of recursion that allows you to reach arbitrarily high energy scales because you, in the end, need to know A. Okay. So okay, I have thought about this for a long time. I didn't come up with a good idea. HPQCD has done this, for example, putting an equal here, and this allows them with the volumes that you have, okay, being able to do this. But there is no recursion between one volume and the other. Whereas here there is a recursion between one lattice spacing at the other. This recursion is done by taking the continuum limit at each step. Okay. So in order to do this, you will need to take the infinite volume limit at each step, and this is very hard. But I mean, sure, maybe there are things to do there. Yes, I don't know. Yes.
And how do the cutoff effects go? It's like proportional to a squared, or do you have like higher order or logarithmic?
Oh, higher order for sure. I mean, this is the cutoff effects. They never go like a square. I mean, they always have higher orders and log corrections, and this is tricky. On top of that, in many of these simulations at finite volume, it can be that you have order A effects, and I will explain this later why. And it is because of the choice of boundary conditions. Okay, but yeah, in principle, if you would be doing the normal thing, okay. So pure gauge, for example, okay, you don't have Wilson fermions, nothing like this, then they will go like A squared with corrections that have logs of alpha at A and many things there.
I mean, I guess that the larger volumes you get, the finer spacing you have, and so you have, I mean, if you go to larger volumes, you have also A to the 4th.
Sure, but take into account that the larger volumes here are not larger than the volumes that you do in CLS. So the cutoff effects, I mean, the lattice spacings here the interest is to go in the opposite direction. You want to go to very small volumes, and that means that your lattice spacing will be 10 to the minus 4 Fermi. Still, since the volume is only 10 times larger than this, you have significant cutoff effects even there, okay? But, yeah?
But then as you do the extrapolation that
Yeah.
you just indicated here,
Yeah.
I mean, you will plot all these points as a function of A over L squared. So you don't need to have some extra quantity to set the scale, and then would be sort of the smallish volumes like the 8 or the 10 that might just deviate from sort of the assumed leading order lattice artifacts of order A squared, for instance, in Young-Williams.
Yeah, exactly. So the thing that guarantees this, as Harmut is saying, is the fact that these couplings definition depend only on L. That means that lambda over L is also constant. So there are no additional cutoff effects. So you can do this extrapolation as A over L squared. So you do them literally, okay? You put A over L, okay? The expected leading behavior is a square, and here you put your G square of 2L, okay? And they should go like this, okay? Maybe the last point will deviate, but there is no extra scale. So there is no A squared times lambda, there is nothing like this, because all the scales are, this only depends on a single scale, okay? So this is guaranteed to work. In general, I would say that the shape of these continuum extrapolations is better than in the large volume world, okay? This is easier, okay? There are several reasons of them. First of all, the logarithmic corrections to A squared scaling, okay? They go as alpha at the scale of 1 over A, and here you are at very high energy scales. That means that alpha is basically constant. So the logarithmic corrections are very small, okay? This is the first reason. The second reason is that the level arm that you have in lattice spacing is much larger. Usually in large volume you hope to have a factor of 2. Here from 8 to 24 or from 16 to 48 there is more than a factor of 2. So I mean, I'm not saying one has to be careful with every extrapolation, but I would say that this case is not worse than what we do.
What is the usual amount of points that's used to do this continuum extrapolation? Is this a reasonable 5 points?
Yeah, maybe you cannot do the 48 everywhere, but yeah. This is the range of, these numbers come from a real case in pure gauge. So yeah. Questions? Okay. So the first part is done, okay? In this expression, okay, I have shown you how you can compute the integrals of the beta function. For this, I take the step scaling function, and I add logs of 2 by steps of 2 in the renormalization scale, okay? And this gives me this 2 to the k here. Now the problem is that this only gives me lambda in units of mu 0. And what is mu 0? Okay, so who the hell knows? Because mu 0 is a particular scale. It will be a large volume scale, okay, because I start this iteration with large volumes. But this defined, for example, by the fact that G squared of mu 0 is 10.7321, okay? This is a finite volume. What it's telling me is that this particular observable, that is not physical at all, okay? When I simulate in a volume that is given by some condition, the value of this observable is equal to 10.73. Okay, so I mean there is no pion mass, no proton mass that I can compute on this lattice in order to know how much is mu 0 in MEV. Okay, so if I cannot compare with experiment, how do I get this piece here? Okay, because I want to pass mu 0 in Fermi or in MEV to the other side in order to really compute lambda. So this is the second step. Okay, is this clear? Yeah.
Before we
Yeah.
go,
Yeah.
I still don't have it here. Where do you use this to compute the integral? I mean, where do you need to plug this number to compute the integral?
Okay, so very good. So let me do one step more. Oh no, I didn't want to. Yeah, I didn't want to remove this. the function sigma, okay, takes g squared of L and takes me to the large volume, okay. This function is invertible because the beta function is monotonous, so sigma minus 1 does the other way around, okay. So now the trick is in this final expression there, okay, the only thing that I know is g squared at the scale 2 to the k mu 0. This appears here, and appears here, okay? So put this in another color. So I need this guy. It's the same, okay? Very good. So I start u0, that is equal to g squared at mu 0, okay? Now I compute u1, that is equal to sigma minus 1, the inverse, okay, of u0, okay? And this will be g squared of 2 times mu 0. U chi is sigma minus 1, okay, of u to the k minus 1, and is equal to g squared at 2 to the k mu 0. So this is the number that you wanted, okay? So I apply the step scaling function starting from the large volume. I go to smaller, smaller, smaller. In the end, I get a value of the coupling with an error, okay? I plug this number of the coupling with the error in this formula. I multiply by the 2 to the k, okay? That I know that I have done exactly k factors of 2, and I get lambda over mu 0, okay?
Yeah, it's good.
Vale, good. Okay, very good. So now the next step is how to compute mu 0. Okay. So again, the matching with the real volume, you will need some large volume simulations like CLS that in fact have to use the same action, okay? Because the matching is always done through the bare parameters, through the lattice spacing, okay? So what are we going to do? I take once more this table of CLS simulations. Okay, there are some kappas here, and I'm going to be easy now, and let's assume that these are the kappas and these are real simulations at the physical point, okay, such that this is really the physical value of the pion mass at different lattice spacings, okay. And now on these lattices I compute one quantity that I use to set the scale. So I am going to compute mu 0 in units of a physical quantity. Let's say the proton mass, f pi, whatever comes in the PDG, okay. So if I do this on my lattice, I get the proton mass in units of A, okay. And now I'm going to put here some invented numbers. So something like 0.63, 0.51. These are wrong, okay. So, but you compute the proton mass in lattice units, okay. This is done by doing the correlator, the usual things that we do, okay. These are large volume simulations because I want really to see the proton, okay, not something in finite volume. So if I quote the L over A's here, okay, these are, I don't know, 48, 64, etc., etc. These are really large volume simulations, okay. So now, in an ideal world, what I would do is to do these simulations at different L over A's in such a way that my finite volume coupling is constant. So imagine that there exists here some, this is CLS, okay. Now imagine that there exists here some other L over A's, okay, such that G squared of L, my finite volume coupling, in fact defined at 0 quark masses, okay, so really a massless scheme, and with the finite volume and the boundary conditions I can do this. I put here a number of points in such a way that this thing is constant, okay. Well, if this happens, I know that for these particular numbers L over A's here, okay, the volume is the same, but only the lattice spacing has changed. And in a massless renormalization scheme, the lattice spacing is given by beta, okay. So now, in these simulations, I could take, if you want, my renormalization scale, that is A times mu 0. This comes from this thing here, this A times mu 0, remember, is equal to A divided by the square root of 8t, okay? And therefore, by this relation that I have left here many times ago, is given, okay? Mu 0 is given by the flow time up to which I have integrated, that is given by L, okay? And I divide it by the values of A times the proton mass that have been computed here in CLS. Okay? In a massless renormalization scheme, the effect of the quark masses, okay, go away when you take the limit, the continuum limit, because basically this is a very short distance quantity. The fact that the quarks are massless or not doesn't matter for this. So this thing gives me mu 0 over the proton mass. And now mu 0 is equal to this thing that I have computed times the proton mass given by the PDG. Okay? End of the story. I have the other ingredient that I needed here. Okay? So let me summarize this part here. What I do here is to use the fact that in a massless renormalization scheme, okay, the same values of betas correspond to the same lattice spacing. Okay? And what I do is to compute the ratio of my renormalization scale over a physical quantity, for example, the proton mass. Okay? Now, in a real world, you have the betas from the large volume from CLS. It will not happen that you can find any points here where this is constant, so you will need to interpolate, to extrapolate, blah, blah. Okay? I mean, that's a different issue, okay? But conceptually, this is what it is, okay? I mean, if you would really like to do this, you will need here a lattice with 20 point times 7 points, and this cannot be done, okay? So, but conceptually, the thing is easy. This is how you do, okay? You can either interpolate the values of the proton mass for the betas that you can compute here with an integer number of points, or you can interpolate these to the others, or the other way around. But conceptually, this is the thing that you do. This thing, yeah? Questions? Yes?
I mean, are they correct? I mean, so technically the lattice spacing not only dependent in reality in beta, but also on kappa, right?
Yeah, but only by cutoff effects.
Yeah,
so my claim is that this limit removes this.
Okay, okay.
So this is how you compute, for example, the ratio of the proton mass at the chiral point over the ratio at the physical point, or something like this, or at the symmetric point over the physical point. How do you do this? You compute A times the proton mass at one point and A times the proton mass at the other. You take the continuum limit, and then the mass dependence on the lattice spacing goes away in a massless renormalization scheme. Yes?
So the beta values are those for the CLS and then you have
Yeah.
the simulations on the other side that are like
The same beta values, the finite volume things.
the same beta values but different.
So the same beta because I want them to have the same lattice spacing up to cutoff effects, so that this thing gives me a continuum limit that makes sense.
So beforehand you said that you want to use pure gauge theory.
Oh, okay. I have here go to a more complicated one. In pure gauge, you forget about this thing here, and this will be exactly the same. So you will compute here some betas that are typical of a pure gauge simulation. For example, with the Wilson action, beta is around 6, okay, 5.9, 6.2, 6.3, okay. And then you will compute, instead of the proton mass, you cannot compute the proton mass in pure gauge, you compute T0, okay. That is a large volume quantity, okay. And now you do your finite volume simulation, and you will relate T0 with the finite volume renormalization scale. And this will allow you to give lambda in units of a square root of T0. In pure gauge, you cannot do anything else, because there is nothing like an MEV pure gauge, not even close. So you can only compute dimensionless quantities. But in pure gauge, you will be able to compute lambda in units of a large volume quantity, like a square root of T0, or the string tension, you can do the same, or whatever you, or R0, whatever you prefer to set the scale with. The key is that in pure gauge, some quantities have to be computed on large volumes where finite volume effects are negligible, okay? And then on this same lattice spacing that you know that is the same because you take the same beta, you move to a small volume and you compute a finite volume quantity. Okay? Yeah. And then you relate the finite volume scale with the large volume one. Okay? So you basically reduce the number of points a lot. You go from 48 to 16 or to 20. Good. Very good. So, I thought that this was the most important thing. Now we have the thing of the boundary conditions, how this really is done, okay? Something prepared there, but the important thing is that you understand this procedure, okay? This is called finite volume renormalization schemes, can be used for quark masses, for BK, for many other stuff, and it solves really the window problem, also for renormalization, okay? So it's a very beautiful construction. And in the case of alpha S, where perturbative corrections are very large, this is a strategy that works very well. Okay? Okay. Now we come back to the choice of boundary conditions. Okay. And this is will be a bit of blah blah blah. Because basically, when you see these works about this, people talk about the Schrodinger functional, about this, about the other background field, and then one might wonder why the hell you are doing these things. Okay, and I think that this is okay, because QCD on a finite volume is complicated. It's not QCD itself. Non-perturbatively, there is no issue, but perturbation theory is very delicate. So let me do it with Jan Mills, because this is the usual. This has all the problems, okay? So this is the usual continuum action or partition function in QCD. And this F mu nu here has two parts. One that is linear in A, and one that is quadratic, that is given by the commutator. Okay? So what one typically does in perturbation theory is so what you typically do in perturbation theory, you are interested in the value of this, of expectation values in the limit that G0 goes to 0, okay? So typically, once you have the action written like this, you scale your fields, okay? This is the leading part, okay? And what you do is you write A mu, you substitute it with a power of G, okay? And then this means that this part here is the leading term. It will give you the gluon propagator, okay? When you take the G here and you put the square, it will remove the 1 over G squared that is present in the action. Okay. This thing will be a gluon vertex that has momentum, and it has a power of G. Okay. In the Feynman diagram, so it will be something like this. Okay. And this thing is the 4 gluon vertex. Okay. And it will be order G squared. Now, once you do this, you can do the usual things of doing Feynman diagrams. Okay. Now, this is the free part. Okay, gives you the propagator. This is the interacting part. The problem is that this general picture is not true on a finite volume with periodic boundary conditions. Okay. Why? Because on a finite volume with periodic boundary conditions, there are special momentum modes of your gluon field that contribute to leading order to the action, not quadratically, but to the quartic power. Okay? So if you do the Fourier decomposition of your gauge field, okay, on a lattice or on a finite volume. This is a sum over x or an integral if you're in the continuum, it doesn't really matter. Okay. And then the zero momentum mode, okay, has this part that is zero. Because the derivative pulls down a p, okay? So for p equals 0, this part is 0. Okay? This part is 0, and the leading contribution of this zero momentum mode to the action, okay, is quartic, not quadratic. Okay? This means that in the same spirit as what you do here to scale a mu with a power of g, okay, in order to get the free part plus the other, what you are suggested to do with the zero mode is to scale it with the square root of g. Whereas the other momentum modes, okay, will be scaled with g. Okay, p different from 0. This square root of g, when you put it in the commutator, gives you a g squared that kills this, and this is the leading contribution of the zero mode to the path integral. This zero mode is not a gauge choice in finite volume, and you can see this that there are gauge invariant operators, for example the Polyakov loop that wraps along your periodic directions. They are gauge invariant, okay, and they are affected by this zero momentum mode. So this is not a gauge degree of freedom. It's not solved by Fadeev-Popov or whatever gauge fixing that you do. It's not an ambiguity, it's physics. Okay? These zero momentum modes are physics. Okay? And moreover, there is an additional problem, that is that the vacuum is a complicated superposition of what are called tolerons. Okay? So there are, if you choose zero momentum modes matrices here that commute, all these have zero action. And this is not unique. The space of matrices that commute, okay, is complicated. So the real vacuum is not like you have a single vacuum and you are doing perturbation theory around it. You have several vacua, and there is the real vacuum, the quantum vacuum, will be a mixing amplitude of all of them. So, okay, I mean, there is a lot of people that have spent a lot of time understanding QCD in finite volume, okay? I mean, probably Pierre Van Baal is one of the people that have studied this more in detail for basically all his life, okay? But basically, you can see that this induces a problem because the limit g goes to 0 is in fact delicate. Okay, so let me try to write here very fast a mock example. So this is a zero-dimensional case. So I'm going to write a partition function . Okay. So now, what is the problem with this partition function? The problem with this partition function is that this is a convergent integral for all value of g larger than 0, but when g is equal to 0, you have a flat direction. That is, when u is equal to 0, okay, all this thing is 1. Okay? And this is not suppressed, it's not damped. So this integral is divergent for g larger than 0. It's convergent for any value larger than 0, but for g equals 0, this is divergent. Okay? Still, expectation values have an integral similar like this, both in the numerator and in the denominator. Okay? So expectation values are finite. This case is very similar to this. Okay? These flat directions here are given by the tolerance, are fluctuations in such a way that the matrices commute. Okay? So now, this is a case that you can solve explicitly. The expectation value, for example, of u squared v squared, okay, is equal to 1/2 plus g squared over 2 plus, or minus, sorry, g to the 4 divided by 2. And then there are here some Bessel functions, k1 and k0. And it might seem that this is a normal behavior in a power series in g squared, like the same that you would expect in a perturbation theory. But in fact, these guys here remember the divergence of this as g goes to 0. And the asymptotic behavior of this when g goes to 0 is quite delicate. In fact, as g goes to 0, this thing is 1/2 plus g squared divided by the log of g squared divided by 2 plus the Euler constant. Something similar happens here in QCD on a finite volume with the SU2 group. These integrals are divergent, and then you get logarithmic corrections to your perturbative series. This means that your observable will no longer be g squared plus g to the 4 plus g to the 6. It will have these terms. Okay? And then you are screwed, because there is no lambda parameter, perturbation theory is a nightmare, and this is all very difficult. Okay? For SU3, the integrals are not divergent, but still the fact that the 0 modes have to be scaled with the square root of g means that there are terms here, okay, like this one times this, that gives contribution order g cube. So you get a square root of alpha. So your observables are not something alpha plus alpha squared plus alpha cube, as something alpha plus square root of alpha plus alpha squared plus. Okay? And then everything, all that we have said since day one, basically breaks down. Okay? There is no universal beta function, there is no lambda parameter, all goes to hell. Okay? So in infinite volume, this is solved, because in infinite volume, the 0 momentum mode, okay, doesn't play any role. Okay? It's a constant field, and then by integrability, this is not there. Okay? It's only a mu, this is 0. Okay? But in finite volume, it plays a role. So then there is people that have studied QCD on a finite volume. Okay? The first papers, in fact, were my PhD advisor. I think that is called, how is it called? Ground state metamorphosis in QCD, okay, by Tony González Arroyo, and then Ancoste, and some people in Marseille, and Pierre Van Baal has studied this for a long time, okay. But there is another direction that was also taken in part by Tony and also by Martin Luscher, that is just choose a boundary conditions where this problem is not present, okay. So instead of using periodic, I'm going to take a choice of boundary conditions such that the vacuum is unique, okay, and that there are no 0 modes. There are 2 choices for this, and I only have time to mention them. So one of them is using what the mathematicians call Dirichlet boundary conditions, and we call a Schrödinger functional. Okay. So what you do is your gauge field at the time boundaries, you fix the values to some boundary fields. Okay? If you choose these boundary fields wisely, you can guarantee that the action has a unique minimum, okay, and that there are no 0 momentum modes. In particular, a choice that you can make, the simple one, is 0 background field, where the ck and the ck prime are 0, okay, yeah, okay. And another choice of boundary conditions that is very used is called abelian background fields. Is where this ck is a diagonal matrix, okay, that belongs to the group SU3, okay, or SU2, then it's a 2 by 2 matrix. Okay. So the case of the abelian background field is traditional, the one that has been used, because you can choose these angles here, phi, okay, to depend on a parameter eta, and then the derivative of the action with respect to this eta, the expectation value of this, gives you the definition of a finite volume coupling that is called the Schrödinger functional coupling. Okay? So basically what you are doing in this game is that you are putting a constant electric field in your lattice, okay? And this electric field feels how large is T in physical units. So when T is very small, okay, this coupling will be very small. When you try to push it apart, it will feel it, because it is measuring how correlated is one boundary with the other, okay? How you feel one boundary from the other, okay? This is what this Schrödinger functional coupling does. So this coupling is very important. Yes, sorry?
Sorry. The L, is it related to T, to the time?
Yeah, usually you take T over L fixed, okay? Equal 1 or 2.
Okay. No.
That's the usual cases, yes.
What is eta?
Eta is the parameter that defines the background field. So basically you put one field here and another there, both of them depend on eta, and then the derivative with respect to eta is measuring you how the energy of the system will change if you change the boundary conditions, if you change the field that is crossing your lattice, okay? And this feels how big is the lattice, and it's a valid finite volume coupling, okay? So this coupling is super important, because in an heroic effort in the 90s, this is known up to 2 loops in perturbation theory, okay? I think that this is basically the only lattice finite volume computation that is known up to 2 loops. I think that this is quite a challenge, okay? In infinite volume, we have other techniques, but in finite volume, these computations basically have more or less to be done by hand. And this is, so you have no integrals, you have sums, and this is complicated, okay? So still, this scheme is used a lot in finite volume studies, because it what gives you the better control. When in the last piece you use perturbation theory, you know this perturbative behavior better, okay? Now, the bad side of this is that the Szymanczyk effective theory tells you that these boundary conditions give you order A cutoff effects, okay? So it's like if you are doing Wilson fermions, but not really improved, and then there is something like CSW that is called CT and CT tilde that you need to compute in order to make your errors scale like A squared, okay? This is not known non-perturbatively, blah, blah. So this is a very long story. I cannot go into the details, but there are also a bad thing associated with this choice, okay? Basically, the reason behind this is that these boundary conditions break chiral symmetry, okay? Even in the continuum, they break chiral symmetry, and therefore they give you order A cutoff effects. Now the other solution is called twisted boundary conditions, okay? And they come from the fact that if you want your physics to be periodic, you don't need your gauge field to be periodic. It is enough that it is periodic up to a gauge transformation, okay? So these matrices are called twist matrices, okay? And again, if you choose them correctly, you can ensure that there is a unique minimum of the action, and there is no tolerance, and perturbation theory is in powers of G squared, as you want it to be. There is a lambda parameter, a beta function, and there is everything, okay? So this thing, since it's a construction that is invariant under translations, okay, does not break chiral symmetry. That means that you don't have any order A effects. But these boundary conditions, they are only compatible with the fermions if the number of fermions is an integer multiple, okay, of the gauge group. Okay? So you can do nf equals 3 or nf equals 6 or 12 if you are interested. But not 4, for example. Okay. This comes back to an old argument by Parisi, in fact. So okay, so I didn't only have time to give you the thing, okay? What I want to say is that there is a motivation why you see papers talking about the Schrödinger functional, twisted boundary conditions and all this, and it's because perturbation theory in QCD with a finite volume is a very complicated business, okay? It's very difficult to reach high orders, it's very difficult to understand what is happening, okay? But non-perturbatively, there is no problem. You can do your simulations in a finite volume, okay? I mean, there are zero modes there, that, but I think that this is, for quantities that are center invariant, I don't think that there is any issue, okay? I mean, still this is a complicated business, it has to be read and all this, but the reasons for this Schrödinger functional in particular, that is something that has been used for many years, are not arbitrary, okay? It's not that people come out one day and say, okay, I want to do this, okay? It's, there is a good reason for this. And it's time, no? Yeah, so thank you very much, and there are exercises there, please.